These are the answers to the AP Chemistry packet on topics 2.1 to 2.4. On this slide, you can see Unit 2 at a glance. Unit 2 is entitled Compound Structure and Properties. In this video, we will take a look at Topic 2.1, Types of Chemical Bonds, Topic 2.2, Intramolecular Force and Potential Energy, Topic 2.3, Structure of Ionic Solids, and Topic 2.4, Structure of Metals and Alloys. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 2.1, Types of Chemical Bonds. Here are some essential knowledge statements from the AP Chemistry course and exam description. Electronegativity values for the representative elements increase going from left to right across a period and decrease going down a group. These trends can be understood qualitatively through the electronic structure of the atoms, the shell model, and Coulomb's law. Valence electrons shared between atoms of similar electronegativity constitute a nonpolar covalent bond. For example, bonds between carbon and hydrogen are effectively nonpolar, even though carbon is slightly more electronegative than hydrogen. Valence electrons shared between atoms of unequal electronegativity constitute a polar covalent bond. The atom with a higher electronegativity will develop a partial negative charge relative to the other atom in the bond. In single bonds, greater differences in electronegativity lead to greater bond dipoles. All polar bonds have some ionic character, and the difference between ionic and covalent bonding is not distinct, but rather a continuum. The difference in electronegativity is not the only factor in determining if a bond should be designated as ionic or covalent. Generally, bonds between a metal and nonmetal are ionic, and bonds between two nonmetals are covalent. Examination of the properties of a compound is the best way to characterize the type of bonding. In a metallic solid, the valence electrons from the metal atoms are considered to be delocalized and not associated with any individual atom. Okay, so now it's time to do a brief exploration of this PhET simulation on the polarity of a bond. And I will put the link to the website in the video description area, and you'll be choosing the two atoms icon that is located on the left side of the screen once the website loads. Okay, so in this simulation we have a bond between atoms A and B, and I have checked the box for bond dipole, which will be indicated by an arrow, and I've also checked the box for partial charges. So partial positive and partial negative charges, delta plus and delta minus. But right now, on the slider on the bottom of the screen, both atom A and atom B have the same electronegativity value. So there is no bond dipole, there's no arrow, and there's no partial positive or partial negative charge. So watch what happens as I increase the electronegativity of atom B relative to atom A. So now we see a dipole, and now we see partial positive charge for atom A and partial negative charge for atom B. So the bond dipole always points toward the atom with the higher electronegativity value, and the partial negative charge is on the atom that has the higher electronegativity. If I want the arrow to point in the opposite direction, what I could do is simply increase the electronegativity of atom A relative to atom B. So now we see the arrow is pointing toward atom A, and there's a partial negative charge on atom A. So I'll go back and switch that. So again, you can see that the dipole, the length of the dipole is increasing as the bond becomes more polar. The arrow always points toward the atom with a partial negative charge, which is the atom that has the higher electronegativity value. Okay, so now I'd like to summarize the information that was presented in that PhET simulation for two atoms. The symbol Delta plus represents a partial positive charge, and the symbol delta minus represents a partial negative charge. The atom with the lower electronegativity value has a partial positive charge, and the atom with the higher electronegativity value has a partial negative charge. We use the term dipole or dipole moment when two opposite charges are separated by a small distance. A dipole is created in the polar covalent bond. The arrow in the dipole points toward the atom with the higher electronegativity value. So in the PhET simulation, you can observe the following. When the atoms have the same electronegativity value, a nonpolar bond is formed. The partial charges and the dipole arrow disappear. And when the atoms have different electronegativity values, a polar bond is formed, and the length of the dipole arrow increases as the difference in electronegativity increases. The longer the arrow is, the greater the dipole moment is, and the more polar the bond is. Question 1. Each of the following bonds is polar. Based on the periodic trends in electronegativity, label each of the following bonds as follows. Place the symbols delta plus and delta minus on each atom based on their relative electronegativity values, and draw an arrow to represent the direction of the dipole in each polar bond. So starting with carbon and nitrogen, they are located in the same period, and electronegativity increases from left to right. So nitrogen is more electronegative than carbon. The partial negative charge is on the nitrogen atom, and the dipole points toward the nitrogen atom. Fluorine and bromine are in the same group or family, and since electronegativity decreases from top to bottom, that means that fluorine is more electronegative than bromine. The partial negative charge is on the fluorine atom, and the dipole points toward the fluorine atom. Phosphorus and chlorine are in the same period. Chlorine is further to the right, so chlorine is more electronegative than phosphorus. The partial negative charge is on the chlorine atom, and the dipole points toward the chlorine atom. Sulfur and oxygen are in the same group or family. Electronegativity decreases from top to bottom, so oxygen is more electronegative than sulfur. The partial negative charge is on the oxygen atom, and the dipole points toward the oxygen atom. Question 2 says, which of the following bonds is classified as nonpolar? So what we're looking for would be a bond in which the difference in electronegativity between the two atoms is very small. So the correct answer is the bond between two fluorine atoms. Anytime you have a bond between identical atoms, then that would be a nonpolar bond because the difference in electronegativity would be 0. All right, moving on to question 3. In this question, we are given a table of electronegativity values. And part A says to arrange each of the following bonds in order of increasing polarity. So from least polar bond to most polar bond. And our 3 bonds are carbon-oxygen, nitrogen-oxygen, and boron-fluorine. So if we look at the table, we notice that all 5 of these elements are in the same period. That makes it very easy to compare the relative difference in electronegativity. So if we start with the least polar bond, that would be the pair of atoms that has the smallest difference in electronegativity. And that would be nitrogen and oxygen, which are right next to each other on the periodic table. And that would be a difference in this case of 0.46. Now, on the other extreme, for the most polar bond, that would be the pair of atoms that has the largest difference in electronegativity. So in this example, the farthest apart, that would be boron and fluorine. And that's a difference of 1.94. So then in the middle would be the carbon-oxygen bond, and that happens to be a difference of 0.95. Now, 2 questions you might be asking based on this particular question. Number 1, do I need to memorize electronegativity values for the AP exam? And the answer is no. And then kind of a related question is, did I really need to know the electronegativity values to answer this particular question? I would say no, you could just look at the comparison since they were all in the same horizontal row. But if the AP exam ever asks you a question in which electronegativity values are needed, then they would provide you with a table to do that. So moving on to part B of this question, I think it is helpful to have these values because now we're looking along certain diagonals on the periodic table where it may not be so obvious which atom has a higher electronegativity. So our choices here for part B are carbon, phosphorus, phosphorus, fluorine, and carbon, chlorine. So here are the electronegativity values for those four elements. Again, same criterion for the least polar bond would be the pair of atoms that has the smallest difference in electronegativity, and hopefully you can see that carbon and phosphorus would have the smallest difference. That works out to be 0.36. And then for the most polar bond, we're looking for a pair of atoms that has the largest difference in electronegativity. So across that diagonal from phosphorus to fluorine, that's a difference of 1.79. That is the most polar bond. So I think to answer this question, it was very helpful to have the electronegativity values and discover that the difference between phosphorus and fluorine is greater than the difference between carbon and chlorine. And again, now we have ranked these three bonds from least polar to most polar. All right, this is question 4. And this question should help you make the connection between the degree of polarity of a bond and the magnitude of the dipole moment of that bond. So question 4, part A asks, which of the following bonds, HX or HY, is the more polar bond? Justify your choice based on the information in the table below. So H is hydrogen, but X and Y are simply unknown elements. The dipole moment is the degree of polarity of a bond, and that is measured in units of dBi, which is abbreviated with a capital D. So what I see here in the table is that HX has a greater dipole moment, 1.82, as compared to HY, which is 0.44. So the answer, which of these bonds is the more polar bond, it's going to be HX. The greater the magnitude of the dipole moment, the more polar the bond is. So since HX has a larger value for its dipole moment, it is the more polar bond. You may recall from the PhET simulation that as the bond became more polar, the length of that arrow representing the dipole increased. All right, now moving on to part B of this question. Now we know the dipole moment of the HBr bond, which is 0.82 dBi, but we have to make a prediction about the dipole moment of HCl. So is that going to be less than or greater than 0.82 dBi? And it says justify your answer based on periodic trends in electronegativity. So since chlorine and bromine are in the same group or family, and we know that electronegativity decreases from top to bottom, that means that chlorine is more electronegative than bromine. Therefore, this is going to be a more polar bond. So the dipole moment for HCl should be greater than 0.82 dBi. Again, chlorine being more electronegative than bromine, that means that the difference in electronegativity between H and Cl is greater than that between H and Br. So HCl is a more polar bond and has a greater dipole moment. All right, before I get to question 5 of the packet, I want to make some general comments about bonding. Here you can see a diagram in which elements are classified as metals, nonmetals, and metalloids. There is an important difference between a covalent bond and an ionic bond. The usual method used to classify a bond as either ionic or covalent is the following. When we have a bond containing a metal and a nonmetal, it tends to be an ionic bond. And when we have a bond between two nonmetals, it tends to be a covalent bond. Now this is a simple criterion that works well for many examples. However, the nature of a chemical bond is more complicated than this. In reality, all polar bonds have some ionic character. And so there is a continuum between the extremes of covalent bonding and ionic bonding. Here we have a particle level view of an ionic substance on the left and a covalent or a molecular substance on the right. An ionic substance consists of positive and negative ions with attractive forces between the oppositely charged ions. A covalent or a molecular substance consists of molecules with attractive forces between the molecules. So ionic substances generally tend to be a solid at room temperature, and they tend to be a hard, brittle solid with a relatively high melting point. They do not conduct electricity as a solid, but they do conduct electricity when they are molten or aqueous, so when they're melted or dissolved in water. A covalent substance can exist as either a solid, a liquid, or a gas at room temperature, and if it is a solid, it is generally a soft solid with a relatively low melting point. And they do not conduct electricity whether they are solid or melted or dissolved in water. Now, here is a situation, this is question 5, in which examination of the properties of a substance is the best way to characterize the type of bonding present in that substance. And so for this example, we have the elements tin, so Sn, which is classified as a metal, and then we have chlorine, Cl, which is classified as a nonmetal. So based on that criterion, metal and nonmetal, you would predict it would be ionic bonding. And so I'm going to give you 2 examples of compounds. One of them has the formula SnCl2, and the other has the formula SnCl4. Let's take a look at the properties of each substance, and this should help us to predict the type of bonding that is present. So SnCl2 is a white crystalline solid. Well, that would suggest if it's a solid at room temperature, it might be ionic. Its melting point is relatively high, 247 degrees Celsius. So that would be consistent with our prediction that it should be an ionic bond or an ionic substance. But take a look at the properties of SnCl4 and it might surprise you. SnCl4 is actually a colorless liquid at room temperature. And it doesn't freeze as a solid until we get down to negative 34 degrees Celsius. So based on these properties, it would suggest it is more likely to be a covalent substance. Again, back to that point about examining the properties of a substance sometimes is the best way to characterize the type of bonding in that substance. Topic 2.2, Intramolecular Force and Potential Energy. Here are some essential knowledge statements from the AP Chemistry course and exam description. A graph of potential energy versus the distance between atoms is a useful representation for describing the interactions between atoms. Such graphs illustrate both the equilibrium bond length, the separation between atoms at which the potential energy is lowest, and the bond energy, the energy required to separate the atoms. In a covalent bond, the bond length is influenced by both the size of the atom's core and the bond order, that is, single, double, or triple. Bonds with a higher order are shorter and have larger bond energies. Coulomb's law can be used to understand the strength of interactions between cations and anions. Because the interaction strength is proportional to the charge on each ion, larger charges lead to stronger interactions. Because the interaction strength increases as the distance between the centers of the ions, nuclei, decreases, smaller ions lead to stronger interactions. So that first bullet point, the graph of potential energy versus the distance between the atoms, is going to be examined. So I have 3 situations for what happens when we have 2 hydrogen atoms. There's too far apart, too close together, and then a stable chemical bond. So this first situation is too far apart. This is not a covalent bond because the hydrogen atoms are too far apart and they do not interact with each other. So the potential energy between the atoms is 0. Now we have a stable covalent bond between the two hydrogen atoms, and the internuclear distance, the distance between the nuclei, is the bond length, and that's 74 picometers. So the potential energy between the atoms is at the lowest point when the arrangement is the most stable, and that's negative 436 kilojoules per mole. So there is a balance right now between attractions and repulsions. The attractions are between opposite charges, between the positive proton of one atom and the negative electron of the other atom. But there's also repulsions between like charges, so between the protons and between the electrons. So there's a nice balance when there is a stable covalent bond. But if you bring these atoms even closer together, now this becomes unstable because the atoms are too close to each other and there's too much repulsion between the like charges, between the positive protons of each atom. So the potential energy now is very high as this is an unstable arrangement. So on the y-axis we see potential energy, and you can see that 0 in the middle. And then on the x-axis we have the distance between the nuclei, the internuclear distance, and that's in picometers. So potential energy, kilojoules per mole on the y-axis, distance between the nuclei in picometers on the x-axis. So on the far right side of the diagram, that is that first example that I had mentioned, where the atoms are too far apart from each other, and therefore the potential energy is 0. Now, as the atoms get closer together, they will form that stable bond. But if they're too close together, the repulsions between the nuclei create an unstable situation with high potential energy. So at the bottom of that valley, the bottom of that minimum of potential energy, that is the stable bond, and that is the arrangement where attractions and repulsions are balanced. So for hydrogen, the bond length is 74 picometers. That's the label on the x-axis for where that particular minimum potential energy is located on the graph. And then on the y-axis, the distance from 0 to the bottom of that potential energy graph, that would be the 436 kilojoules per mole. That is either the energy released when the two hydrogen atoms come together to form the bond, but it can also be the magnitude of energy that is absorbed when that stable hydrogen-hydrogen bond is broken and we pull the atoms apart. So in number 6, we have a similar kind of graph, but this is not for two hydrogen atoms. This is for two chlorine atoms. So number 6 says, the diagram above represents a graph of potential energy versus internuclear distance for two atoms of chlorine. Part A, the length of the Cl-Cl bond, again, that would be on the x-axis at the position of that minimum potential energy. So looking at the graph, that would be around 200 picometers. That's the distance between the atoms. And then on the y-axis, from 0 to the bottom of that little valley, that would be approximately around 240 kilojoules per mole. And I'm not going to say it's a negative number because I'm referring to the magnitude of the energy. The energy, 240 kilojoules per mole, is the energy required to break the bond or the energy released when the bond is formed. Question 7. Question 7, as well as question 8, is asking us to make a prediction about the bond length and the bond energy. And these are bromine atoms as well as iodine atoms. So we should remember the periodic trend in atomic radius as we go from top to bottom down a group. So there's fluorine, chlorine, bromine, and iodine. Those are the halogens. And as we go from top to bottom, the atomic radius increases. So therefore, based on the periodic trend in atomic radius, the bromine atom has a larger atomic radius than the chlorine atom. Now, what is that going to do to the length of the bond? Well, if the atoms are larger in size, then the distance between their centers will be larger as well. So we're looking for a longer bond length between two bromine atoms as compared to the chlorine, and then a shorter bond would be more difficult to break, so therefore would require more energy to break. A longer bond is actually easier to break and requires less energy. Since we've already decided, based on periodic trends, that the bromine-bromine bond should be longer, then it's going to be easier to break and should have a lower bond energy. Now that we've made our prediction, let's take a look at that graph of potential energy versus internuclear distance. And here are the numbers. The bond length for chlorine is 200 picometers. The bond length for bromine is 228, so it is a longer bond. The bond energy for chlorine is 243 kilojoules per mole, and then the bond energy for bromine is 193, so it is a lower bond energy. If we look closely at the appearance of the graph, we have the solid line representing chlorine and the dotted line representing bromine. If you look closely at the x-axis, you can tell that the bromine-bromine bond has a longer bond length because the location of that valley, that minimum in potential energy, has shifted toward the right along the x-axis. So it is a longer bond. Now for the y-axis, if you look at that diagram and you compare chlorine and bromine, you can see that the graph for bromine has a minimum of potential energy that does not go as deep as it does for chlorine. So the depth of that minimum in potential energy is a little more shallow, therefore requires less energy to break that bond. Now as we move on from chlorine and bromine, let's go ahead and finish it off by thinking about what iodine's properties would look like. So the atomic radius of iodine is even larger than that of bromine, so therefore the distance between the atoms would be even longer. The bond length of the iodine bond should be longer than it is for bromine, and the bond energy should be even less than that of bromine. So here are the numbers for iodine. 266 is in fact a higher number than 228, so it is a longer bond, and 151 is less than that of 193, so it is easier to break and has a lower bond energy. Okay, so up until now, in questions 6, 7, and 8 of this packet, the only types of bonds we've been considering are single bonds, whether it was chlorine, bromine, or iodine. Here, as we prepare to answer question 9, we're considering the possibility of multiple bonds. So bond length and bond energy, which can be affected by the size of the atoms, they can also be affected by the number of bonds that are formed between two atoms. So in this example, we have carbon bonded to carbon, and we have a single bond, a double bond, and a triple bond. So the bond order is referring to the number of electron pairs that are shared between two atoms. One shared electron pair, single bond, bond order of 1. Two shared electron pairs, double bond, bond order of 2. 3 shared electron pairs, triple bond, bond order of 3. Focus on the data for bond length and bond energy. And what you can see as you go from top to bottom in this table is that as we go from a single bond to a double bond, they're getting shorter in length. We go from 154 picometers to 134 picometers. So a double bond is shorter than a single bond. Now look at the bond energy. 614 is higher than 348. So that bond requires more energy to break. It is a stronger bond. When we compare a triple bond to a double bond, they get even shorter and even stronger. So 120 is less than 134. That's a shorter bond. 839 is larger than 614. That is a higher bond energy, therefore stronger because it requires more energy to break. So what's the general trend? As we go from single to double to triple, the bonds are getting shorter. So the bond length is decreasing and they're getting stronger. The bond energy required to break the bond, increases. Okay, as we prepare to answer questions 10 and 11 in this packet, I'm going to switch gears from talking about covalent bonds to talking about ionic bonds. So ionic compounds, they have relatively high melting points. And this is because the attractions between the ions and the solid crystal are very strong. So we have this crystal lattice of positive and negative ions. Another measure of the strength of the attractions between the ions is known as the lattice energy. Now, lattice energy can be defined as the energy required to separate 1 mole of a solid ionic compound into gaseous ions. So in this particle diagram, you can see on the left, we have a solid crystal lattice of ions, and on the right, these ions have been separated from each other, and they're very far apart. So for sodium chloride, 788 kilojoules per mole is absorbed when we pull the ions apart from each other. Lattice energy can also be defined as the energy released when the gaseous ions combine to form 1 mole of a solid ionic compound. But whether that is absorbed or released, the magnitude of the lattice energy is related to the strength of attraction between the ions in the crystal lattice. The greater the magnitude of the lattice energy, the stronger the attraction between the ions in the crystal lattice. Now, this does bring up a good application of Coulomb's law. You may recall, when you were studying periodic trends, which was topic 1.7, you learned about Coulomb's law, and Coulomb's law describes the attractive or repulsive force between 2 charged particles. So back when you were learning about atomic structure and periodic trends, it was about the attraction between the nucleus and the electrons. Now, we're not talking about the nucleus and the electrons. We're talking about the attraction between positive and negative ions in an ionic compound. But it's the same relationship in that there is a numerator and a denominator. The numerator is about the magnitude of the charges on the ions, and the denominator is about the distance between those ions in the crystal lattice. So take a look at these 2 particle diagrams side by side. Hopefully you can tell that they appear to have roughly the same size in terms of the positive and negative ions, but the particle diagram on the right represents a greater magnitude of charge. So you can see +2 and -2 for the charges on the ions as compared to +1 and -1 on the left. So which of these compounds would have a greater lattice energy? Well, the diagram on the right represents the compound with the higher lattice energy, and that's because it has a greater charge magnitude. That's the numerator of Coulomb's law. Greater charge magnitude, stronger attractive forces between the ions, and a higher lattice energy. Now let's take a look at these 2 particle diagrams. The ions have the same magnitude of charge. They're all +1 and -1, but on the left we have smaller size of ions, so they are closer to each other in the crystal lattice. And on the right we have larger size of the ions, so the distance between them is farther apart. Which one's going to have a greater lattice energy? Well, the particle diagram on the left has a smaller distance between the ions. That's the denominator in Coulomb's law, so it's going to have stronger attractive forces between the ions and a higher lattice energy. So number 10, we can summarize those 2 trends. The magnitude of the lattice energy of an ionic compound tends to increase as the magnitude of the charges on the ions increase and as the distance between the ions in the crystal lattice decrease. Now we're going to see an example in number 11 of each of these properties. All right, so for question 11, we are given a lattice energy for sodium fluoride, NaF. So it's 930 kilojoules per mole. Part A, do you predict that the lattice energy of sodium chloride, NaCl, should be less than or greater than 930 kilojoules per mole? So what we're going to do is look at the periodic table, compare the size of fluorine with the size of chlorine, and then make our choice based on that. So both fluoride and chloride are -1 in terms of their charge, but chloride is larger in size. Remember that size gets bigger as you go down from top to bottom. So chlorine, as in the atom, as well as chloride, the ion, has a larger ionic radius than that of fluoride. So the distance between the ions in sodium chloride is greater than the distance between the ions in sodium fluoride. So according to Coulomb's law, if the distance between the ions increases, that is a weaker attraction between the ions, so sodium chloride should have a lower lattice energy. You may recall it's actually 788 kilojoules per mole, so I actually kind of spoiled that number by giving it as an example earlier, but based on Coulomb's law and atomic radius, we have a larger distance between the ions, resulting in a weaker attraction and a lower lattice energy. All right, now on to part B. Magnesium oxide, MgO, is it going to be higher or lower for its lattice energy? Is it higher or lower than 930? Well, since magnesium's charge is +2 on the periodic table, and oxygen's charge is -2, that would mean that we're talking about a greater magnitude of charge. That leads to stronger attraction between the ions in MgO as compared to NaF. So our prediction is greater than 930 because of that greater magnitude of charge for the ions in MgO. Topic 2.3, Structure of Ionic Solids. Here is an essential knowledge statement from the AP Chemistry course and exam description. The cations and anions in an ionic crystal are arranged in a systematic, periodic, three-dimensional array that maximizes the attractive forces among cations and anions while minimizing the repulsive forces. Let's take a look at question 12 from your packet. You can see that there is a portion of an ionic crystal. This is lithium chloride. You can see that periodic three-dimensional array with oppositely charged ions packed together in this crystal lattice. And we have to identify which of the ions is lithium and which of the ions is chloride. If we look on the periodic table and we can count the number of electrons for each ion, that's how we can answer this question. So lithium plus is going to be 2 electrons, whereas chloride, Cl minus, is going to be 18 electrons. So the correct answer is that lithium will be the smaller ion and chloride will be the larger ion based on the number of electrons and the occupied energy levels. Now, you might assume that the positive ion should always be smaller in size than the negative ion. Let's take a look at question 13. Here we have a very similar question, but our example is cesium fluoride. That'll be Cs plus and F minus. Again, let's count the electrons. So F minus will be a total of 10 electrons, and cesium, Cs plus, will be a total of 54 electrons. So because we have a greater number of occupied energy levels, the cesium ion will actually be larger in size than the fluoride ion. So what's nice about question number 13 is that it reminds you to count the electrons and consider the energy levels in the shells. The positive ion will not necessarily always be smaller in size than the negative ion. All right, let's take a look at question 14. Sodium chloride, NaCl, contains positive and negative ions. Explain why solid NaCl does not conduct electricity. And then question 15, what are 2 changes that can be done to an ionic solid, such as NaCl, that will enable it to conduct electricity? You may recall in an earlier video, we were talking about why certain chemicals behave as electrolytes or non-electrolytes. So it's the ions are present, but they are locked in that rigid crystal lattice, and they are not free to move and flow. So number 14, the ions are held in fixed positions in a rigid crystal lattice, and they are not free to move and flow. So the solid does not conduct electricity. The 2 things that you could do to get those ions moving is to either dissolve the ionic solid in water, or you could melt the ionic solid and turn it into a liquid so that now the ions are free to move and flow. All right, question 16. A particle diagram for solid magnesium sulfide, MgS, is shown below, but this particle diagram is incorrect and contains several different errors. Identify all of the errors in the diagram. So the first thing that I notice about this particle diagram is that all of these positive ions are right next to each other in this crystal lattice. So we know that they need to be arranged in such a way that opposite charges are attracted to each other and like charges repel. So these positive and negative ions should be arranged in an alternating pattern. Again, because like charges repel and opposite charges attract. Another change that we can make to fix this diagram in terms of a mistake is if you look on the periodic table and you find that magnesium is in group 2, the charge on magnesium should be 2+ instead of 1+. And then oxygen and sulfur are in the same family. Oxygen and sulfur have a charge of -2, so the charge on the sulfide ion should be 2- instead of 1-. Finally, as we saw in the previous questions about particle size, we should consider the number of electrons to decide which ion is larger or smaller. So since magnesium 2+ has 10 electrons, and sulfur 2-, the sulfide ion, has 18 electrons, the magnesium ion should be smaller in size than the sulfide ion. So those are the mistakes that are present in this diagram. Here's what it should look like. So now you can see that we have an alternating pattern of ions, positive and negative. We have magnesium with 2+ and sulfur with 2-, and the magnesium ion is smaller in size than the sulfide ion. All right, so one more thing I'd like to mention about the property of ionic solids is they tend to be brittle and they can be cleaved along well-defined planes. So in the diagrams, you can see what happens when a stress is applied to an ionic crystal. It will cause the ions to slide over just slightly, and then repulsion between ions of like charges leads to separation of the layers. Again, ionic solids can be cleaved along well-defined planes. So take a look in the video about how that occurs.
Here, a small crystal of solid sodium chloride is shown. It is transparent and has 90-degree angles at the sides. When a knife blade is placed on it parallel to one side and tapped with a hammer, the crystal cleaves into 2 pieces, each with a very clean plain edge. Now the piece that was cleaved off of the original piece is examined. The knife blade is placed on it at a 45-degree angle to a side and tapped with a hammer. The crystal shatters, but part of it cleaves parallel to a side.
Now in this video we can see a computer animation to illustrate why these ionic solids can be cleaved along well-defined planes.
In this atomic scale view of sodium chloride, when the crystal is struck, ions with the same charge are moved near each other. Since like charges repel, the crystal cleaves into 2 pieces along the plane where it was struck.
Topic 2.4, Structure of Metals and Alloys. Here are some essential knowledge statements from the AP Chemistry course and exam description. Metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons, that is, a sea of electrons. Interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial spaces between the larger atoms. So, for example, with steel, in which carbon occupies the interstices, or the spaces in between the atoms of iron. Substitutional alloys form between atoms of comparable or similar size, radius, where one atom substitutes for the other in the lattice. In certain brass alloys, other elements, usually zinc, substitute for copper. Question 17. Explain why a metallic solid can conduct electricity. Here in this particle diagram, you can see that we have the metal ion, the nucleus and the core electrons, that's positive, and then we have this sea of mobile valence electrons where the electrons can move. So metals are good conductors of electricity because there are valence electrons that are able to move and flow and are delocalized throughout the entire crystal lattice. In addition to being good conductors of electricity, metals are malleable, which means they can be pressed or hammered into flat, thin sheets, and they are also ductile, which means they can be pulled or stretched out into long, thin wires. So unlike an ionic solid, which is very brittle and cleaves along well-defined planes, as I showed you earlier in the video, here For a metal, when a stress is applied, the atoms can easily slide past each other, and this explains why metals are malleable and ductile. So the ability of metals to be deformed and change their shape can be explained by the fact that the metal atoms, they form bonds to many other neighboring atoms within this sea of mobile valence electrons. So when there are changes in the position of the atoms, that's a relatively easy thing, and the electrons are just redistributed around the collection of atoms. And you can see this with something like aluminum foil, where you can crunch it and stretch it and do all kinds of things to change the shape. All right, and the last thing that I'd like to talk about in this video is metal alloys. So a metal alloy is a mixture of two different metals, or possibly a mixture of a metal and a non-metal atom. And the two types of alloys that you have to know in AP chemistry are substitutional and interstitial. In a substitutional alloy, that's formed between two different atoms whose atomic radius values are similar to each other. So one example of a substitutional alloy is brass, which contains a mixture of copper and zinc. And you can see in this table that since the atomic radius of copper and zinc is the same, and even if they're not exactly the same, if you have two atoms that have very similar atomic radii, then a substitutional alloy is formed. So you can see that all these circles are about the same size. Now, moving on to an interstitial alloy. This is formed between two different atoms in which the atomic radius of one atom is much smaller than that of the other. So now what happens is that the smaller atoms can fit in the empty spaces in between the larger atoms. And so one example of an interstitial alloy is steel, which contains iron and carbon. So looking at this diagram, you can see that the black atoms represent carbon, which has a smaller atomic radius than the gray atoms, which represent iron. So an interstitial alloy is often stronger than the pure metal because the presence of these smaller atoms in the empty spaces, that makes it more difficult for the atoms of the metal to move and slide past each other. So that's why steel is harder than iron. All right, well, this brings us to the end of the video. I hope that these answers and explanations were helpful. Thanks for watching.